Today, we're re-diving into the mind-bending science of black holes, breaking down every step of a journey into these cosmic monsters, from the outer edges of their gravitational pull to the infinitely dense singularity at their core. This is not just science fiction. This is the real physics of the universe, proven by Einstein's equations, observed by NASA's most powerful telescopes, and studied by the brightest minds in astrophysics. To understand what happens when you fall into a black hole, we first need to understand what a black hole actually is. A black hole is not an empty void in space, as many people think. It is a region of spacetime where gravity has collapsed in on itself to an infinite degree, created when a massive star reaches the end of its life. When a star, at least 20 times the mass of our Sun, runs out of nuclear fuel, it can no longer fight against its own gravity. The star's core collapses inward in a fraction of a second, crushing matter into a tiny, infinitely dense point. The outer layers of the star explode outward in a brilliant supernova, one of the brightest events in the universe, leaving behind only the collapsed core, a black hole. These are called stellar mass black holes, the smallest and most common type, with masses ranging from 5 to 100 times that of our Sun. But there are far larger black holes too, supermassive black holes, which sit at the center of nearly every galaxy in the universe, including our own Milky Way. The supermassive black hole at the heart of the Milky Way, named Sagittarius A multiplied by, has a mass 4.3 million times that of the Sun, yet it is only about 17 times wider than our Sun. These cosmic giants are the key to understanding how galaxies form, grow, and evolve over billions of years. Now, let us begin your hypothetical fall into a black hole. We'll start with a stellar mass black hole first, because its effects are far more violent and immediate. As your spaceship approaches the black hole, you won't see it directly. Black holes don't reflect or emit light, so they are invisible to the naked eye. But you will see the distortion of light and space around it, a phenomenon called gravitational lensing. Stars and galaxies behind the black hole will appear warped and stretched, their light bent around the black hole's intense gravity, like a cosmic lens. You will also see a bright swirling disk of hot gas and dust surrounding the black hole, known as an accretion disk. This material is pulled toward the black hole by its gravity, heating up to millions of degrees as it spirals inward, emitting intense X-rays and visible light that glow brightly against the dark cosmos. This accretion disk is the only way we can see a black hole from Earth, and it is one of the most stunning sights in the universe. As you get closer, the first terrifying effect kicks in: tidal forces. Tidal forces are the difference in gravitational pull between 2 points in space. On Earth, the Moon's tidal forces create ocean tides, but near a black hole, these forces are trillions of times stronger. For a stellar mass black hole, the gravitational pull on your feet, if you re-falling feet first, is exponentially stronger than the pull on your head. This extreme difference in gravity stretches your body like a piece of spaghetti, a process scientists call spaghettification. Your bones, muscles, cells, and even atoms are pulled apart by the unrelenting tidal forces long before you ever reach the black hole's event horizon. You would be torn apart into a stream of subatomic particles, a cosmic noodle dissolved into the void before you even cross the point of no return. It is a brutal, instantaneous end, and it is the fate of anything that strays too close to a small stellar mass black hole. But what if you fall into a supermassive black hole, like Sagittarius A multiplied by? The story changes dramatically here. Because supermassive black holes are far larger, their tidal forces at the event horizon are much weaker. The event horizon of a supermassive black hole is millions of kilometers from its core, so the difference in gravity between your head and feet is negligible at that distance. You could actually cross the event horizon of a supermassive black hole intact, feeling no pain, no stretching, no immediate danger. You wouldn't even realize you crossed the point of no return. There's no sign, no alarm, no physical sensation to tell you that you can never go back to the universe you left behind. This is one of the most counterintuitive facts about black holes. The bigger the black hole, the gentler its entrance. Now, let's talk about the event horizon, the most famous boundary in astrophysics. The event horizon is the point of no return, the distance from a black hole's core where the escape velocity exceeds the speed of light. Since nothing in the universe can travel faster than light, anything that crosses this line is trapped forever. Einstein's theory of general relativity explains this perfectly. Gravity is not just a force, but a curvature of spacetime. A black hole warps spacetime so severely that at the event horizon, spacetime itself bends into a closed loop. There is no direction you can move up, down, left, right that leads back out. Every path you take leads only toward the black hole's core, the singularity. As you fall past the event horizon of a supermassive black hole, the world around you begins to warp in ways that defy human intuition. Time and space swap roles. In our normal universe, time moves forward steadily, and we can move through space freely. Inside the event horizon, space moves forward like time, and you can no longer choose your path through space. You are forced to move toward the singularity, just as we are forced to move forward in time on Earth. The light from the outside universe still reaches you, but it becomes more and more distorted, blue shifted to intense, blinding frequencies as it falls in with you. If you look back toward the universe you left, you would see the entire future of the cosmos unfold in a fast-forward blur. Stars would be born and die, galaxies would collide and merge, and the universe would age billions of years in a matter of moments, all because of the extreme time dilation caused by the black hole's gravity. To an observer watching you from a safe distance outside the black hole, something even stranger happens. Due to time dilation, your fall would appear to slow down more and more as you approach the event horizon. You would seem to freeze at the edge of the event horizon, your image fading and redshifting into darkness, never actually crossing the line. The observer would never see you enter the black hole. You would be permanently stuck in their view at the event horizon for all eternity. This is one of the most mind-blowing paradoxes of black hole physics. Your experience is a continuous fall into the void, while the outside world sees you frozen forever at the edge. As you draw closer to the singularity, the tidal forces finally catch up to you. Even a supermassive black hole's gravity becomes infinitely intense near its core, and you will eventually experience spaghettification, just like you would near a stellar mass black hole. The singularity is the heart of the black hole, a point of infinite density, infinite curvature, and zero volume. All the matter that ever fell into the black hole is crushed into this single, infinitesimal point, where our known laws of physics break down completely. Einstein's general relativity no longer applies here, and quantum mechanics takes over, creating a gap in our understanding that scientists have been trying to fill for decades. We have no way to observe the singularity directly, and we may never know exactly what lies inside it. It could be a gateway to another universe, a loop in spacetime, or simply the end of all existence as we know it. This leads us to one of the greatest mysteries of black holes, the information paradox. Quantum physics tells us that information can never be destroyed, only transformed. But if matter falls into a black hole and is crushed into the singularity, what happens to the information that makes that matter unique? In the 1970s, Stephen Hawking proposed that black holes slowly evaporate over trillions of years, emitting a faint form of radiation, now called Hawking radiation. If black holes evaporate completely, does the information inside them vanish forever? This paradox has puzzled physicists for 50 years, and it's one of the biggest unsolved problems in all of science. Solving it could unlock the secrets of quantum gravity, the theory that would combine general relativity and quantum mechanics to explain the entire universe, from the smallest atom to the largest black hole. NASA and astronomers around the world are working every day to learn more about black holes, using tools like the Event Horizon Telescope, which captured the first ever image of a black hole in 2019, and the James Webb Space Telescope, which studies the accretion disks and environments of supermassive black holes in the early universe. These missions are not just taking pictures, they are testing the limits of our physics, rewriting our understanding of space-time, and showing us that the universe is far stranger and more wonderful than we ever imagined. Black holes are not just cosmic monsters. They are cosmic laboratories, teaching us about the fundamental rules that govern everything we know. Falling into a black hole is a one-way trip with no return, a journey into the unknown that pushes the boundaries of science and imagination. It is a reminder of how small we are in the face of the cosmos, and how much there is left to discover. The universe is filled with mysteries, and black holes are the most captivating of them all, dark, powerful, and full of secrets waiting to be uncovered. As we continue to explore the stars map, the cosmos, and unlock the secrets of space-time, black holes will remain at the center of our greatest questions. They challenge us, inspire us, and push us to reach further into the void than ever before. Please like, comment, share, and subscribe to the channel.